Plan really does a very good job. The first here is talking about black body. Black body is actually empty. Is an empty cavity and with the opening. So in here has kind of certain temperature. This particular black body with a tiny hole in it, any light coming in, it will be captured. Any light coming in, it will be captured, cannot escape. This feature is considered as a black body. So now the black body per se, suppose here is a black body is a complete sphere, have a hole in it. So you heat up this cavity, and it will emit photon coming out. So if this is have a color temperature T sub K, like a 3,000 degree Kelvin. And they using this to moderate this feature. And Planck is doing very good job on this. And the best item about the lighting is tungsten. Tungsten light is like this. Tungsten light is resemble like red body radiation. So using this model, we can calculate a lot of phenomena about the red body radiation related with the color temperature. So the first thing he talking about is the total power. Total power emitted. Total power of emitted radiation. Emitted radiation increases with temperature. This temperature is T sub K, so that there's things they looking at. And then the power is equal to sigma A times E times T to the 4. For black body, E is equal to 1. Black body E is equal to 1. Sigma is a Stefan's constant, and that is the black body radiation depends on the color temperature. And the second one is when it radiates out, this radiation, it depends on wavelength and depends on the maximum. So the peak wavelength is the peak of wavelength means with the maximum and peak wavelength means maximum radiation. The radiation at the one wavelength have a maximum. This particular wavelength is related to lambda max times T. T again is color temperature. In that case, is equal to a constant that equal to 2.898 times 10 to minus 3 meter Kelvin. This type of theory can be derived in the upper junior or senior physics classes, but not for you for this time. So if you do that, so here is the radiation pattern. This radiation pattern depends on the color temperature. So let's say this is from 0 micron to 0.4 micron, and then to the 0.7 micron. The reason why we emphasize these two wavelengths, one is called 0.4, and then another one is 0.7. Between here, we call visible light. And then after the 0.7 micron is called infrared. And before 0.4 micron, in which cases we designate as ultraviolet. The ultraviolet is a portion of light will damage your eye. That's one of the suggestions. You should wear the eyeglass, the polaroid sunglasses, to cut down the radiation into your eye. This one theory has a name. Is a Wien. In the book, it didn't give you this name, W-E-I-N. The Wien's displacement law. Basically, he do one quick derivative and getting the thing done. So basically, the ultraviolet go to. This is the higher the color temperature. This might be TK equal 4,000 degree Kelvin. 4,000 Kelvin. So the more color temperature high, you shift to ultraviolet. The more or the less color temperature will shift to the infrared. That equal to 3,000 degree Kelvin. And then gradually shift. It's obeying this Wien displacement law, meaning the peak wavelength. This is a peak wavelength. Or this is a peak wavelength like this. Now this blue line satisfies this equation. The blue line satisfies this equation. The lambda maximum times the TK is equal to the constant. So what did Max Planck did next things? He do, in order to derive that equations, he considered each wavelength, each wave is a particle. So it's called photon. Each wave is a particle. So the particle had originally is a wave. Then each wave you got to have a wavelength, and then you got to have what we call energy. So called energy carrier. By the energy carrier, they are using quantum theory. That's what it does, meaning that each light wave and signal that is come from the wave, and each wave is considered is energy carrier. So the wave have a frequency. The energy is related with the frequency. So in that cases, he says they quantize. So this is his signal. This N is called HF. F is the frequency of the wave. And then N is an integer. So the photon is a treat a photon as a particle, but at the same time, photon have a wave nature. The wave nature has a frequency. So each photon carry the energy like this. NHF. H here is a Planck's constant. H is equal to Planck's constant. Constant. So he using this model to building the blackbody radiation model up, and then based on this model, he deriving all the equations. So from this, the wave displacement law, I have the calculation formula or example is 28.1, 28.2. We would like you to look at it. And that's a part of the exam. Example number 28.1, 28.2. These two like you to look at it. Another major thing is Einstein. Einstein developing another theory. Einstein is very lucky. He got the Nobel Prize in the early age, so that he enjoyed all the glory for his rest of life. So some people is lucky, some people is not. So what he is they call photoelectric effect. 28.2 is photoelectric effect. It has the phenomena, but nobody can answer this. And then finally, Einstein explained what's going on there. So in this things is he could draw the circuit, so like this, and then this is basically is a photo cell set up. So the light coming out and hitting this photosensor material, and then the electron come out. Here the electron come out. And the electron come out and develop voltage as well as current go through. This is a plus and here's minus. He's using this to do the experiment. And then certain things is number one, they observe dependence of a photoelectron kinetic energy on light intensity. That means that the classical prediction is more intensity, then will give you more current. But in certain cases, no matter how intense the light intensity is, doesn't increase the current. And that is the most contradiction. That means classical prediction is electrons should absorb energy continuous from the electric EM wave, means light. A more intense light should transfer energy into metal faster, and the electron should be current should be more. But the experimental result is the maximum kinetic energy of the photoelectron is independent of light intensity. Is independent of the light intensity. No matter how much light intensity go into it, it doesn't do anything. The next thing is the classical prediction is when the electron related with electron, and the experimental result is no electron are emitted if the instant light frequency fall below some cut-off frequency. So that means electron, the photon carries certain energy, has to be